Hi listeners, welcome to the video lecture series on simulation of solid state drives. In this video, we are going to see how to simulate a voltage source inverter which is required to drive a induction motor. So let me start the procedure for simulating it. Go to new, open a new Simulink blank model. You'll get an untitled screen like this. Let me go to the library browser. In the library browser, you go to Simscape. In the Simscape, electrical, under electrical specialized power systems. Under specialized power systems, go to power electronics and take the IGBT with diode and put it on the screen. Rotate it comfortably. It looks something like this. And double click on this. Remove this show measurement port. Click apply and give OK. And I need 6 IGBT of same structure. So I'm just copying 6 of the IGBTs. So let me connect this emitter with collector, this emitter with collector, this emitter with collector. Let me connect all these collectors together like this. And similarly, let me collect all these emitters together like this. Now I need a DC source, for which again you go to sources. Under sources you have a DC source. Take this DC source, connect it to the top and bottom of the three-phase inverter which we are trying to design. Double click on this, give an amplitude of 650 volts as DC supply, and go to, I need a power GUI. Since this is all power electronics based, I take a power GUI, and I need a load which is available in the passives. Under passives, you go to series RLC branch, drag it and put it on the simulator. I need 3 such loads because it is a 3-phase. So connect all the 3 together. And this is supposed to be connected to the middle of the first leg. This is supposed to be connected to the middle of the second leg. And this is supposed to be connected to the middle of the third leg. Now double click on this load, take an RL load, assume that resistance is of 100 ohms and inductance is of 10 millihenries. So have all these 3 same values, put RL 100 and 10, 110, and again the third one also put RL 100, 10. Now I connected all this. Now in order to view the output of this particular simulation, I need measurements. So again go to Simulink library browsers. Under Sim Power Systems you have sensors and measurements. I'm much interested to know about the voltage, so I have a voltage measurement. Try to take 2 voltage sources, one to measure the line voltage, other one to measure the phase voltage. So line voltage is to be measured between 2 lines, and phase voltage has to be measured between a phase and a neutral. So this is supposed to be the phase and this is supposed to be the neutral. I want to have the RMS value of this particular uh, uh, load voltage. So for which I need an RMS block, which is again available in the same block. So I take an RMS block and put it on the screen. So this is an RMS block, and I connect it to the output of this resistance. I mean this voltage measurement and also output of this voltage measurement. Double click on this RMS block and change the initial fundamental frequency as 50 and initial RMS value of 0. Do this for the other RMS block also. This is again 50 and 0. Now let me have a display unit to display this result, and let me take this Simulink Sinks. I have a display, take it out, put it on the screen, connect it, and this is supposed to be the line voltage and this is supposed to be the phase voltage. So this is line voltage. So let me type this here, line voltage is supposed to be the phase voltage. Phase voltage. Now I need a scope to view the line and phase voltages. So let me go to a scope, take it and put it on the screen. I put a scope here, and this is supposed to be the for this, and I need instantaneous values, so I can put before RMS value, not after the RMS value. After the RMS value, again the same display only will be displayed there. Now this is comfortable. Okay, now in order to trigger this devices at any point of time, no two devices on the same leg should be turned on. So whatever the signal applied here should be not of this. So I go to Simulink library browser, go to commonly used. Here I have a logical operator. Take a logical operator, put it outside, take this and convert it into not, rotate it comfortably so that you can place it on the screen here. So this is one, and this is for the next one. I put a rotation again so that it can be easily connected like this. This is for the second one, and similarly for the third one again I will rotate and connect it safely. Let me have reduce this size of it. Let me connect it like this, and this also I'll reduce the size so that it will be much easy for us to connect. So this and this should be shorted, this this should be shorted, and this and this should be shorted. Now I need a comparator here to compare the sawtooth waveform with the sinusoidal reference. So let me go for a relational operator. Take a relational operator, change this to greater than or equal to, connect it here across the first, again here, and again here. Yes, I have three comparators for three reference waveforms. Now I need a sawtooth waveform generator for which you can use uh, repeating sequence block. Repeating sequence block is available in the Simulink sources. You can go to repeating sequence and connect it. This repeating sequence should have a value of, as given here, 0, put a square bracket, open a square bracket, 0, 1 by 5000, 1 by 5000 by 4, and the third value is 1 by 5000 by 2, 1 by 5000 by 2, and the next value is 3 by 5000 by 4, 3 by 5000 by 4, and the last one is 1 by 5000. So this is capable of generating a triangular waveform starting from 0 to -1, and from 0 to -1 to +1 again. It will have a frequency of 5 kilohertz, 0, 1, 0, -1, 0, -1, 0. This is how I put the values, click apply and give OK. Now the same waveform has to be given to all the three modules. So I connect it like this, and the third one also. So this is how it looks like. Now let me have a little bit reduce the size of this so that we can understand actually how it is being connected. So this is how it looks like. Now here I am supposed to give the reference wave. We know that reference wave is constructed by using magnitude as well as the frequency and phase. So I take a mux block which is available. I can have mux. Yeah, this is mux is available. I can have a mux. I take a constant, and this is supposed to be the magnitude of the constant, magnitude of the sine wave, and I need a frequency. So for which I give 50 hertz frequency. 50 hertz frequency has to be multiplied with 2 pi f because I need only radians per second. So for which I go to a gain block, 2 pi multiplied with 50. So 2 pi 2 into pi multiplied by 50. So this is supposed to be the value, and I integrate this. This is 2 pi actually. I integrate this, for which you have an integrator in commonly used integrator, because I need the theta from omega. So I integrate. So I connect like this. So this is supposed to be the all the three complete one. So let me put it somewhere here. Okay. Somewhere here. We keep it in the comfortable screen. I select everything and move it right side so that it looks comfortable for me to work out more. And this is now here. Okay. Now I take a function block which is available in MATLAB. One second, it is available at user defined functions. In user defined function, you have FCN function. You take this function I supposed to uh, select all this, select all this, and let me drag it to the right side of the screen so that I can work out comfortably. Now this is the first one. This has to be given as u of 1 into sine of u of 2, sine of u of 2, which is magnitude into sine of this 2 pi f into t. This is actually the first reference, and second reference is supposed to be the same one, but with minus 2 into pi, 2 into pi by 3, 2 into pi by 3. Again, close the bracket somewhere here. Yes, minus 2 pi by 3. The third reference is supposed to be the same one, but with plus 2 pi by 3, plus 2 pi by 3. So connect all these three here, connect all these three here, connect this, and this is supposed to be the first reference. This is supposed to be the second reference, and this one is supposed to be the third reference. So all the three references are connected to the inverter reference waveform. This is how the inverter simulation construction is. Uh, yes, now the complete simulation has been built. Now let me run the simulation for 0.1 second. Let me run the simulation, and you could able to see that line voltage is 488 volt and phase voltage is 282 volts. Now again, I can change this to a lower value, say for example 0.9. Again, I run the simulation. You could able to see that this particular value of voltage might have been got down from 488 to 469, and similarly the phase voltage also might have been reduced. So I can change this to a lower values and take different values of phase and line voltage for this modulation index. This block is where we could able to change the modulation index. So different values of modulation index, I could able to see the line voltages and phase voltages as given in the documentation. The documentation is shown here. You could able to fill up, vary the modulation index, note down the phase voltage value and line voltage value. So this is where you want to change the modulation index, this value. This is actually MA, the modulation index, and changing this will result in a change of line and phase voltages, which you want to observe and plot it, and tabulate it as shown in this documentation. Also, you need to plot this waveform. We have to show this waveform. This is line voltage waveform, and this one is supposed to be the phase voltage waveform. These two waveforms also you are supposed to make a M file and convert that into a figure and put it in the document. Thank you for your patient listening. Thank you.